In this video, I'll be doing a detailed solution to the maths question you see on the screen here from the 2024 Cambridge A-Level mechanics paper, specifically paper 4.1. If you're looking for a different question from this paper or a different paper entirely, check out the description below for links. And if you find this video or any of the videos on my channel useful and you want to help the channel out, what helps the most is sharing this video, especially if you're in a class group with other people sitting the exam. Also, I do appreciate likes, subscribes, or even a super thanks. In question 3, we're told a story about a train going up a hill. So let's draw that as simply as we can. Bottom of the hill, top of the hill. Let's make a nice triangle for that. So a train goes up the hill. We get lots of information. Let's write some of them out. The mass of the train is 180,000 kilograms. The length of the hill is 1.5 kilometers or 1,500 meters. The angle of this hill, 1.5. Don't draw that correctly. If you drew that correctly, it'd be way too small. It'd look like that or something. You can't work with it. Exaggerate these small angles that they give us. What else have they told us? They've told us this train has to overcome resistance to get up the hill. That'd be air resistance, friction on the rails, mostly those two things. And that resistance adds up, the work for that resistance adds up to 12,000 kilojoules. And they tell us the speed at the start is, 45, and the speed at the end was 40. Find out how much work the engine of this train did to get it up the hill. There's two ways to do this. There's two ways for a lot of mechanics. Usually energy is one method and forces is the other method. This sort of question is the more famous one where it's quite easy to do both, or it's very manageable to do both. I'm going to do the energy way, but I'll spell out at the end the force way a little bit. But I'll spend most of the time doing the energy way. So the trick here is we're going to talk about conservation of energy. I'm going to look at two worlds. I'm going to look at the beginning and the end, the start of this situation, the end of this situation. And I'm going to work out the energy involved. And in between, that's what they're asking about. That's the work done by the engine. They told us about the resistance done in between. So when we find out what the energy is at the start and we find out what the energy is at the end, the difference between those two has to be the resistance, and the resistance took work out of it. Well, that's not technically true. The resistance worked against us, whereas the engine added energy in. So that's the way I think of it. So let's start the first part of the world, down the bottom here. There's no potential energy, we're at the bottom of the world. The kinetic energy down here. So kinetic energy is equal to a half m is 180,000 times v squared. V is 45 squared. So all of that works out as 182,250,000 joules. But just notice that they did talk about work and energy in the same units. They did talk about kilojoules. So we don't want joules. So let's from now on work in kilojoules. Let me just double check those numbers. Kilojoules. Again, there's no potential energy at the start. So the total energy in this system at the start is this number. At the end, let's call that 2. At the end of the world, we have let's do kinetic energy again. Kinetic energy is equal to a half the mass of the train. I'll use 180 this time, so I get kilojoules as my answer. 40 squared, and the kilojoules at the end, the energy at the end is 144,000 kilojoules. So we really just need to know what's the potential energy. So I just need this height, because potential energy is equal to mass times gravity. We know mass, we know the mass, we know the gravity is 10, and we just need this height. So this is just equal 180 times gravity is 10, and the height is simply, what have we got here? We have the hypotenuse is 1,500, so it's sine. It's 1,500 meters. That's 1.5 kilometers. 1,500 meters. I guess I could have also used 1.5 and left in the zeros here. Anyway, this time sine 1.5. Put all that into a calculator and you get 70,678 kilojoules for total energy at the end here of 214,678 kilojoules. So we started with this, we ended with this. What happened? And it's easy from here. That's all the hard work done. What happened? The start of the world, 182. You can add to either side you want. So I like to think of what did we add to this world or take away from it to get the answer of 214,678. What did we add and take away to this? We know what we took away from it. That's easy. They tell us it's 12,000 kilojoules was taken away from this system by the resistance, air resistance or friction, and something was added in. We'll call that the engine, the work done by the engine, W, and that's what they're asking us to find. So it's just a matter of rearranging this. W is equal to this minus this plus this. Do that out on your calculator and you will find 44,400. That's the three significant figures. 44,428 kilojoules. Or if you would rather three significant, this is fine, this is full marks. 400 is also full marks. We rounded off somewhere, didn't we? We rounded off in this point here. That's why we get to this 8. I think this was 6. I have it here somewhere. 6, 7. Instead of 6, 7, 8, it's 6, 7, 7, 7, 6, 0. Anyway, that's your final answer. That's the work added in by the engine. Oh yeah, I was going to do it the other way as well. You could, let's set it up here. You could think of this as a force question. Halfway up the hill, let's think, or in the hill here. What's happening this train? Well, gravity is working against it, or some gravitational force is working against it. Some resistance force is also working against it. They tell us about that. They tell us the work by it was 12,000. Again, work is force times distance. So we know the distance here involved. So this 12,000 kilojoules of work, we know how much force that resistance must have been. Again, I don't care if it's friction or it's air resistance. Either way, we know some force working against it in that direction. We know gravity's working against it in this direction. What's left is we know the engine must be doing something. And we know overall that the system slows down. It has a deceleration from 45 to 40. So we can find out the overall force of the system to cause this acceleration. Because we know the mass, we know the acceleration. So we know the overall force. We just add up all of these to find out what the force of this engine must have been. And then remember that they ask for work. So once we find the force of the engine, multiply by 1,500 meters and you'll find the work. You know what, next time I do one of these questions in a different paper, I'll do it this method. So if you want to check out my channel for a different question, because these come up every year, I'll do the next one by force. Okay, that's question 4 done. If you have any follow-up questions, let me know in the comments below. I'll do my best to get back to you. Thanks for watching and have a great day.